This is an example problem of conservation of momentum with a collision in 2 dimensions. This example is written out on the notes for October 27th at the end of the day. It's an example problem we didn't have time to do, so check the slides to see it written out. But the situation is there are 2 hockey pucks on an air hockey table that have equal masses of 100 kilograms, and they're colliding, and it's an air hockey table, so we're ignoring friction. So we'll just draw our 2 pucks, puck 1 and puck 2. Puck 1, prior to the collision, is traveling in a direction that can be considered the plus x-axis at an initial velocity of 1 meter per second. So I've written v1 comma I to indicate that it's the initial velocity of puck 1, and it has a mass of 100 grams, and that's 0.1 kilograms. Puck 2 travels in the minus y direction at a speed of 2 meters per second prior to the collision. So v2I is 2 meters per second, and it's in the minus y direction. For v1, it's in the plus x direction. Now, the way I've drawn it, obviously these 2 things aren't going to run into each other, but if they do collide, so the initial position of puck 2 would be up here at the top of the page. This is before the collision, okay? So this is what the momentum of each of those 2 pucks is before the collision. Then they collide. Bang. After the collision, the situation is puck 2, let's just write the mass of puck 2 up here, it's also 0.1 kilograms. After the collision, puck 2 travels 30 degrees above the plus x direction. So this is the x direction. It's traveling this way with a velocity v2 final of 0.8 meters per second. And the question is, what is v1 final? What is the speed and direction of puck 1 after the collision? Well, there's no friction, so there are no external forces acting on these 2 objects. So the momentum of this system before the collision has to equal the momentum of the system after the collision. Here's puck 1 after the collision. We don't know which way it's going. That's what we need to figure out. So if there's no external forces, momentum is conserved, so the change in momentum is 0. That means P final, the final momentum, is P initial. These are vector quantities, so what we need to do is take into account the x and y components. So that means P final x is equal to P initial x, and P final y is equal to P initial y. I can't change momentum from going in the x direction to going into the y direction without some external force. It's not the same momentum if the number is different, but the direction is different. If the number is the same, but the direction is different. So let's take the x equation and write it out. What is the momentum of each object? It's m1 v1 final x. That's the momentum of this guy after the collision, plus m2 v2 final x. That's the x component of the momentum of this guy after the collision, and that equals the initial x momentum. Well, initially, things are a little bit easy because particle 2 is only traveling in the y direction, particle 1 is only traveling in the x direction. So the only initial x momentum I have is m1 times its initial velocity, v1I. There is no x component to the initial velocity of puck 2, so before the collision, I have no x momentum from puck 2. I only have x momentum from puck 1, so that's my total x momentum. And in fact, I have the numbers for m1 is 0.1 and v1I is 1 meter per second. So that gives me 0.1 times 1, or 0.1 kilograms meters per second, and it's in the plus x direction. So that's my x equation. I know my two m's also, so the only thing I'm missing are v1fx and v2fx. Well, I'm given the final velocity of puck 2 after the collision. So let me write in my masses: 0.1 v1fx plus 0.1, that's the mass of puck 2, times v2fx, the x component of puck 2 after the collision is the x component of this velocity vector, is v2 cosine 30. So that's 0.8 times cosine of 30, and that equals 0.1 kilogram meter per second. So now I have everything I need to get the x component of the velocity of puck 1, and I can solve that. v1fx is 0.1 minus 0.1 times 0.8 times cosine of 30 divided by 0.1. And when I solve that on my calculator, I get that v1fx is 0.31 meters per second. So that's the x component of the velocity of puck 1. Now, let's take a look at what the y component is going to look like. So I'm going to write my y momentum equation. P final y equals P initial y. The final is m1 v1 f in the y direction plus m2 v2 f in the y direction equals my initial y momentum. And before the collision, the only particle that had momentum in the y direction was particle 2. So that's m2 times v2I, and that's in the minus y direction. So that gives me minus 0.1 times 2, or minus 0.2 kilograms meters per second. That's the initial y component of the momentum of the whole system. It's entirely contained in puck 2. Because only puck 2 has motion in the y direction, puck 1 is moving in the x direction before the collision. Again, I know m1 and I know m2, and I can figure out v2fy. So I have 0.1 v1 fy plus 0.1, and v2fy is the y component of puck 2 after the collision. That's v2 times sine of 30. It's opposite the angle. So that gives me 0.8 times sine of 30 equals minus 0.2. Again, then I can solve for v1 fy, the y component of puck 1 after the collision, and I get that's minus 0.2 minus 0.1 times 0.8 times sine of 30 divided by 0.1. And when I put those numbers in my calculator, I get v1 fy is minus 2.4 meters per second. So the question asks, what is the final velocity vector, v1f total? Well, the magnitude of it, v1f, is the square root of v1fy squared plus v1fx squared from the Pythagorean theorem. So that is the square root of 2.4 squared plus 0.31 squared. The minus here doesn't matter, it's getting squared, so it becomes a positive number anyway. So that gives me slightly, it's mostly in the minus y direction. That gives me 2.42 meters per second. And the direction of it if I'm drawing puck 1, it's got an x component of its velocity that's in the plus x direction, v1 fx here, 0.31, and its y component is minus 2.4. It's down like that. Minus 2.4 meters per second. So the total velocity is this guy here. And if I want to specify the direction, I'll use this angle theta. The tangent of that angle theta is opposite, or v1 fy, divided by adjacent, or v1 fx. And that gives me theta is inverse tangent of 2.4 divided by 0.31. So 2.4 divided by 0.31. And take the arc tangent, and I get 83 degrees. So the final velocity is 2.42 meters per second, 83 degrees below the positive x direction. Let's ask ourselves if this makes sense. Our initial momentum is to the right from puck 1 and down from puck 2. We've got more downward momentum than we have rightward momentum because this puck is traveling faster than this one. After the collision, we have puck 2 going to the right and up, but not very fast. Our initial momentum was entirely down and to the right, so we're going to have a downward component for puck 1, and we have a little bit of a rightward component for puck 1 to make up for the fact that this one is going kind of slowly, and a big downwards component for puck 1 to account for the fact that this one's going up a little bit. So qualitatively that makes sense, and we trust that we were careful with our math here to get the numbers right.